This class will be discussing on reverse phase chromatography or hydrophobic interaction chromatography, which is used for downstream processing application. Reverse phase, we mean to say actually that mobile phase use is actually more polar than the stationary phase. So stationary phase in this case will be mostly hydrophobic. Support material will be there. Maybe in this case, for example, we can use silica, which is coated with some hydrophobic functional lights. And the organic phase, I mean to say the liquid phase, will be some of the organic solvent, polar in nature, maybe water, methanol, acetonitrile, those kind of things. Now the name reverse phase actually arises because it was the second variant in the time span when the chromatography came into picture. It was the second one. Then what was the first one? First one, or we can say the normal one, that was having a polar stationary phase, and the mobile phase was less polar. That is the traditional one. So the reverse phase came when we are changing the nature of the stationary phase, the opposite one. Then that's why it is called reverse phase. There is no other reason behind this nomenclature. Now typical reverse phase, if I am going to have a chromatographic system, then we will be using some stationary phase which is actually bonded with silica support. We can have different functional groups like amino, phenyl, cyano, C4, C8 or C18 phases. So basically there is a long chain of hydrocarbon which is making it hydrophobic. So amino is still hydrophilic in nature, phenyl is moderately hydrophobic, and cyano, C4, C8 and C18 is increasingly order, they're becoming hydrophobic in nature. Now the second point what we need to highlight or maybe we need to understand is hydrophobic interaction chromatography. Actually the structurally, or maybe you will say the component wise, they are not really different. The reverse phase and HIC are very similar, but the density of the ligands molecule, or maybe the binding, or maybe surface functionalization, degree of surface functionalization is much lower in hydrophobic interaction chromatography, because reverse phase chromatography, the degree of those kinds of functional group is too high, and if you are having some globular protein, they will tend to denature. So reverse phase chromatography may not be useful for large molecule or macromolecular structure. Now we'll show you in this coming slide how the Rp chromatography is really working in the system. We'll have here one diagram. You can see where the reverse phase is, the surface is coated with maybe hydrophobic functional lights, and a globular protein is coming to attach. So essentially the hydrophobic functional lights, if exposed area, we will say the hydrophobic patch is actually interacting with the surface, and it will be bound with the hydrophobic surface until or unless we are having some solvent which is going to replace it. So we need to have some organic solvent reaching some specific concentration, then it will kick it out. So the elution process, when you are going to elute the compound from the column, we need to change the polarity of the solvent to take it out. Now if you are talking about the column, we need to understand what kind of columns we can be used. So basically we can have different kinds of functional groups attached to it. Maybe you can see in here we can have some C18 hydrophobic phase, which is very much useful, for example in between a 2000 to 3000 Dalton peptides. So it is actually long chain. But if I am having some small functional groups like C4 hydrophobic phase, it can be useful for peptide greater than 3000 Dalton, or maybe for proteins. The particle in this column are usually made up of silica, which is robust, stable, and in the most solvent and within pH range of 2 to 8, they are all very much effective. But if we need some broad pH, then we can use some polymeric support or alumina, which can work from highly acidic pH 1 to pH 13 range. They can be useful. Now two things we need to also give some idea. So we are normally using some small pore silica, which is actually going to result in inferior protein separation, while if I'm having some wide pore silica, it can fully interact in the surface, give its better separation, because the globular protein must have the surface exposed, they must interact with the support material or maybe adsorbent. So if I'm having small pore, then possibly the whole globular protein structure is not accommodated, they cannot really interact. So we need to have somehow a larger or wider pore size is important. Similarly, I'll discuss over here, when we are making the functionalization, you'll see that some of the silica surface silanol groups SiOH functionalites, you can see some of the functionalites are not really capped, because the C18 hydrophobic phase, they cannot come because there is too much crowding, or we will say this is actually inhibiting the functionalization of some of the silanol groups. So in that scenario, we need to actually cap it. So that's why we're discussing here, as the silica is modified with some hydrocarbon molecule to create a hydrophobic surface. So we can have some chlorosilyl groups is attached with hydrocarbon chain. So we can have some octadecyl chlorosilyl. Maybe we are going to have the octadecyl chain length is going to bind. But if it is not completely done, then what we'll see, some of the patches will have some hydrophilic groups still there. For example, SiOH functionalites, which actually remain unreacted, or which could not be functionalized in this process. Now, what kind of mobile phase we will be using? We can have during this process, we can use some mobile phase. We can use gradient, the amount of organic solvent we can precisely control, and we can reach some concentration where the protein is actually getting dissolved from the hydrophobic surface. And we can have in most of the time, depending on the hydrophobicity of your compound, we may have a gradient in mobile phase, may be useful. We most of the time also use acetonitrile, and some of the time we will be using methanol. The reason is very simple. For acetonitrile, it is volatile, it is low viscosity, so back pressure is not too high, it is transparent to UV plane, so these solvents can be useful. And if you are using some very much hydrophobic protein, then isopropanol can be used. But isopropanol is having viscosity more, it can cause some back pressure in the system. Now, till now we were discussing about reverse phase chromatography. Now, little bit change we will be discussing is hydrophobic interaction chromatography. Though it is very similar, maybe seemingly not much different, but maybe the principle may be a little bit different, we need to know. So HIC is actually exploring the interaction of hydrophobic groups attached to a matrix and hydrophobic patches present in your protein, because in most of the time we will see that protein molecules, if we want to have some 3D structure, if you see it, most of the hydrophobic groups of the proteins are actually buried inside the 3D structure, so they are not in surface, and only hydrophilic groups are exposed. We'll show probably here. You can see one protein structure we are going to show here. Maybe the red coloration when I am giving in the protein chain, there maybe we assume they are hydrophobic functionalites. So you can see they are all inside the core of the structure, and the green chains are actually hydrophilic. They are interacting with water. So when it is interacting with water, they will cause a hydration cell. So water molecule is actually putting a coverage on that. Now in this case, it is very hard to interact with any hydrophobic matrix. It is not possible. So there can be one alternative option here. The alternative is that addition of salt. So if we add some amount of salt, then salt is likely to interact with the bound water molecule. So they will interact with the bound water. So water will be removed, or water cell from the protein will be removed. So essentially, if water is removed, at that time the hydrophobic patch will be exposed finally. So if the hydrophobic patch are exposed, so it can now, you see, the hydrophobic patches has come outside and they can bind with the ligand very effective way, or we can say the interaction can be positively channelized. Now HIC is a milder technique because distribution of the hydrophobic patches is also very important, and we can see the recovery is also comparatively higher. In some protein, some stability may be a problem, so in that case we can increase of retention time may be required, because if I am using some salt over here, maybe stability of the protein can be a problem. So we need to know what salt concentration you use and what are the support matrix we are using. It can be agarose, dextran or cellulose based matrix we can use for our column based HIC. But if I am going to have some HPLC, then preferably we will be using silica based matrix or gel, which is having small uniform size. And commercially you can have octyl or phenyl saccharose can be used in HIC column. Now HIC is equilibrated with ammonium sulfate, maybe less than 2 molar, along with maybe or 1 to 4 molar of NaCl solution. So this is the first equilibration of the column. Then you are loading our sample, which will be followed by decreasing salt concentration or increasing the polarity to elute the protein. So that will actually take out the protein out of the system, because we already told you, if we are increasing salt, then only interaction is happening. If we decrease the salt, then those proteins which were already attached to the hydrophobic surface can be released. And finally we can use high concentration of urea, for example 6 molar urea, to take out any impurity which is already bound with your column. Actually for cleaning and reuse, rather we say, the column can be reused if we treat it with high concentration of urea. For example 6 molar of urea, we can reuse the column. So that's all for the day. We can discuss the other chromatographic technique. Primarily in this case we will be using gel filtration chromatography in our next presentation.